Okay, hi guys. So in this lecture, we'll be discussing more on the calculation of entropy change. So let's get started. So now we'll be seeing for a reversible phase change at a constant temperature and pressure. How do we derive the entropy change? For reversible phase change at constant pressure and temperature, let's see a case in which dqp as equals to dh. We already know. Then ds can be written as dqp upon t. So this can be also written as dh upon t. Okay, so or simply delta s can be written as delta h upon t. So we have this reaction for phase change, xs converting into xl. Okay, so this, let's say this is the delta s of fusion, which would be equals to delta h of fusion upon temperature. Temperature would be nothing but melting point, because we are converting solid into liquid, so we are converting it at melting point. So we can write delta S fusion for S12 would be equals to delta H fusion divided by T of melting point. Okay, now the case of equilibrium, when both the phases coexist, then here, as both phases are in equilibrium at melting point or freezing point, equilibrium at melting point or freezing point, so we can write delta S fusion would be equals to S of xl minus x s of xs. Okay, and also we can write that delta S of fusion can be written as negative of delta S of freezing. What would be the delta S of freezing? Delta S of freezing would happen when the reaction, or whether rather the conversion of xl into xs takes place. Okay, and x delta S of fusion is just the reversal of that, so we can write minus here, as s is a state function. Okay, we can also write that delta fusion or molar entropy at fusion would be equals to delta fusion hm upon t. Okay, now let's see another case, which is case number 2. So in here we can write that suppose xl is converting into xg, so here delta S of vaporization can be written as delta H of vaporization upon temperature of, or rather boiling point. Okay, this is the entropy of vaporization. Okay, and we can also write that delta S of vaporization would be equals to x times g, S of xg minus S of xl, and similarly delta S of vaporization would be negative of delta S of condensation. Condensation is the reversal of this reaction in which xg converts into xl. and XL and XG both phase are in equilibrium at boiling point. Okay, next let us see conversion of graphite into diamond. This is graphite and conversion of graphite into diamond. Okay, so here we have delta S transition would be equals to delta H transition upon temperature. Temperature is the transition temperature. Okay, and similarly entropy change in a chemical reaction at constant temperature. Entropy change in chemical reaction at constant temperature can be written as delta Rs would be equals to summation of let's say gamma p times S of mp minus summation of gamma r S of m r, where Sm is the molar enthalpy, rather entropy. Here we are using S. So Sm is molar entropy. Okay, and these are the stoichiometric coefficients of the reaction. This is the stoichiometric coefficient of products, and gamma r is respectively for the reactants. And at standard states we can write that delta r S naught would be equals to summation of gamma p Sm naught p minus summation of gamma r Sm naught r. Okay, so similarly we can also write that delta Rs naught can be equals to summation of gamma p delta formation of products minus summation of gamma r and entropy of formation of reactants. So just remember them. Okay, where delta of F S naught would be equals to standard entropy of formation. Okay, so with this we come to the end of this lecture. We'll be seeing more on the change in enthalpy and more examples on the same in the next lecture. So till then, good luck and goodbye.